Great. Well, welcome everybody to this last session. I know that we're all that stands between you and lunch, so we'll try and keep to time. We're going to talk today a little bit about automotive software development and virtual platforms. My name's John Taylor. I'm from Imperas Software. I'm joined by Adachi-san from NSITEXE, and we had help from our partner Shimbo-san at eSol Trinity to put this presentation together. So I'm going to kind of set the scene a little bit, set the agenda up, talk about what's going on in automotive, why RISC-V for automotive, where do virtual platforms fit. Adachi-san will talk through some real-world use cases and how this has worked for NSITEXE with some of their customers, and then I'll try and do a short wrap-up as we get to the end. So when we think we've heard quite a little bit about automotive already over the last couple of days. When we think about the development landscape for automotive, it's probably one of the most complex ecosystems out there in terms of end products. And you've got multiple vendors across all areas of the stack, mixing open source, chip developers, commercial software houses, tier ones such as Bosch, Continental, Denso, OEMs such as the BMWs, Fords, GMs of the world. And the software stack varies considerably in complexity. On one hand, you have kind of very simple microcontrollers, have a simple software stack, maybe running AutoSAR, and a limited amount of applications on top of that. But as we know, cars are getting more complex. We're moving to domain controllers, we're merging functionality, we're introducing hypervisors, so we're running more applications on top of that. And then you move towards autonomous and ADAS functions where you're perhaps, or infotainment as well, and you're perhaps bringing in some open source software into that. You're mixing Linux up with that as well. And we've also got companies going vertical now and doing their own silicon, doing their own software stacks on top of that. But again, probably bringing some open source components into it too. And getting all of those software stacks working when you don't have silicon is really, really hard. And that's where virtual platforms come in to make it possible. So thinking about RISC-V and automotive, we've got some advantages. We've got some disruption happening in the industry at the moment. We're moving from the value being around the metal in the car to the value being the software, software-defined vehicles. Compute requirements are growing. End of Moore's law, domain-specific architectures are becoming relevant. You need efficient compute. Power still matters in EVs. More power in the compute means reduced range, so it's important to have efficient compute in their domain-specific architectures. And actually, automotive is very heavy around open standards and cooperation, and RISC-V is all about that as well. So we're used to working in those collaborative environments and working in the open. At the same time, there are some challenges too. As I showed on the previous slide, the automotive industry is really complicated, and actually you need to get buy-in across all of those players to get them to believe RISC-V will work for them and we can build successful RISC-V solutions. The V model of development is, you start from specifications, you work down to implementation, you work back up, you verify and validate. It means it's quite slow. These things take time to work. And there can be concern as well about the immaturity of RISC-V. Automotive development, yes, it's getting faster, but it's still taking 5 years, possibly more, to get from that initial RFQ for a chip to seeing that chip in driving around the country. To introduce the companies briefly, so Simon talked about Imperas earlier, so I won't run through this in too much detail, but we've been involved in EDA for a long time. We've been doing models for a long time, sometimes for different architectures, RISC-V more recently. And we've been working with most of the ecosystem who are doing RISC-V to provide modeling solutions for them. Demand's evolved. You need high quality models. You want virtual platforms. You need to verify your cores. And now our models are used in pretty much every RISC-V processor project. eSol are our partner in Japan. We work with them very closely, and they work in turn with our customers very closely. And they provide tools, solutions, and services to meet the needs of the customers over there. Again, they're domain experts. They know our technology. They know the market as well. And so with that, I'll hand over to Adachi-san to introduce NSITEXE and talk a little bit more about some of the use cases.
Hello. Thank you, John. Yeah. My name is Koji Adachi. I worked at NSITEXE in Japan. So I'm a manager of own RISC-V core development team. So today, I'd like to talk to you about how virtual platform helped us when we developed the automotive semiconductor IPs. So about this works, all of them worked with Imperas and our Japanese agent, iterate. So before we start, let me briefly our company overview because you guys may not know our company well. So, sorry. NSITEXE is a 100% subsidiary of Denso. Denso is an automotive tier 1 company, and we are developing the semiconductor IP for automotive. This includes RISC-V-based accelerator IP, ML, AI accelerator IP, and security IPs. And as for RISC-V IPs, in 2020, we have developed the first product which has 16 hardware threads and which supports the RISC-V vector instruction, a part of RISC-V vector instruction set. And next year, 2021, we have reused our previous work, and we have launched the first standalone 32-bit RISC-V core as well as A3D products. In the recent few years, we have reorganized our product brand named under the Acaria. So Acaria is not only for the automotive area, but also the other industrial domain we are aiming. And this is a target domain of Acaria NS family. NS means the code name of RISC-V core. And as I mentioned, we automotive company, so we are target for the automotive area, but we'd like to utilize our knowledge like functional safety, real-time operation, or something like that. Anyway, we'd like to utilize our knowledge for the other industrial domain like a smart factory. Anyway, it's too long, so let's go back to today's topics. So today, I have prepared 3 use cases. And fortunately, we don't have much time to go into the deep detail, but all 3 use cases are real use cases when we have developed the semiconductor IPs. So what use case is used for the proof of concept phase? So when we wanted to add the small AI inference accelerator into the existing automotive microcontroller, we needed to show how it looks like. It looks like means how the software works. In that case, we have to we need to show the virtual environment. But you may know the automotive microcontroller has a proprietary vendor-specific instruction set architecture, like Renesas RH50, Infineon Tricores, or something like that. Anyway, we have to combine the heterogeneous instruction set architecture with one virtual environment. And it's a little bit hard to develop such an environment, but we used OVP World Simulator, and it has various CPU models, so we can easily to develop this environment. And as a result, we run the small AI network on this environment, AlexNet, and we can show our customer, and we can discuss about them. This is the first our use case. And this is the second use case. Second use case is performance estimation tools. So yeah, after proof of concept, when we promote our new AI, new accelerator to customers, we need to show how software works well. How works well means how the benchmark score is good or not. So if the customer customer benchmark is open source, it's no problem. It's easy. We can evaluate by ourselves, and we can submit or provide the benchmark result to customer, and then we can discuss the customers. But automotive customers, they do not want to share the detail of their applications, their benchmarks. So mostly they develop their application in privately. So we can not evaluate customer benchmarks by ourselves. So we need to develop such an environment. And the left side figure shows our CPU pipeline model. It has a 3-way out-of-order superscalar model. And it's hard to develop the exact performance models because the hardware is complicated. But we had to provide the customers. So we use the Imperas simulator. Imperas simulator has extendability of performance estimation. And in this case, we only have modeled 2 things. Middle figure, instruction latency modeling and memory hierarchy modeling. It's not complicated. We only implemented 2 things, but to be honest, the accuracy of this performance estimator is not so good. So sometimes error ratio becomes 200 or 300%. But in our cases, it's okay because performance improvement is much better than such errors. RISC-V vector parallelization achieves 10 times or 20 times performance improvement. So this is the second use case for us. And the third use case is the last one. This is the SOC and FPGA preliminary environment. This use case is prepared for the software engineer. And I think this is a very common use case, not so special use case. But in my opinion, it is most practical use case. So as I mentioned, semiconductor IP development requires a very long time period, very long development period, especially automotive area. And on the other hand, software as well. And John mentioned automotive software stacks becomes very thick, very many layers. So especially low-level software need to be started in the early development stage, even the real hardware is not available. So to overcome these situations, we have developed the detailed modeled virtual environment. And Imperas simulator is very good for the detailed CPU modeling. So we have only modeled some peripheral models around the CPUs. That is our third use case. And in addition, for the software development, we used this environment for the hardware verifications. So we provide the hardware verification engineer to this environment, and hardware engineer make a verification test program on this environment. That is our use case. Okay, so I have explained 3 use cases today, and each phase has their own challenges, own difficulties. The appropriate tool overcomes each challenges. That is my presentation.
Okay, thanks, Adachi-san. So yes, to kind of wrap up, I mean, a lot of it was already presented in that last slide, actually, and it was really nice to see the timescales there, showing across the product development life cycle, actually, the different use cases and how they fit together. And we can see that, whether it's architectural exploration, performance estimation, production software development, virtual platforms have a place throughout that. And actually, you know, even when the product's deployed in the field, if you're trying to investigate field failures, models are much more debuggable and much more reproducible than trying to do things on hardware. So we can see, you know, they reduce that time to market, they reduce risk, and they improve product quality. So to conclude, you know, automotive is a really complex supply chain and software ecosystem, possibly the most complex market out there to address. It's going through a massive change at the moment, moving from mechanically defined vehicles to software-defined vehicles, and the amount of that software is growing exponentially. And that's a fantastic opportunity for RISC-V to differentiate. You know, we've got so many things in our favor in terms of customization, allowing folk to differentiate, and actually changing architecture. You know, Adachi-san touched on those proprietary architectures already in use in automotive. They're used to jumping around, so jumping to RISC-V shouldn't be too hard for them to think about. So I'd just like to say thank you very much. I know it's lunchtime and I'm sure you're keen to get down there. Our contact details are on there. Imperas has a booth downstairs. If you want to follow up with us, please come down and talk to us afterwards. Thank you.